Oh, dark matter is something astronomers can deduce it must exist. It seems to have gravity. It seems to be responsible for our existence.
After 45 mind-blowing years beyond the edge of our solar system, NASA's Voyager 1 has shocked the scientific community once again. A Nobel Prize-winning researcher has just revealed that this pioneering spacecraft, launched in 1977, has stumbled upon a discovery deemed impossible by experts. Could this data revolutionize everything we thought we knew about interstellar space? With fresh signals streaming in from billions of miles away, one thing is certain: Voyager. One's latest revelation might overshadow all previous milestones forever. Voyager 1 had a truly dramatic start when it launched on September 5, 1977. Even though it left Earth 16 days after its twin spacecraft, Voyager 2, it ended up moving faster and soon took the lead. This was no small feat given the tight deadlines and limited budgets of the time. Scientists knew that a special alignment of the outer planets would let them use each planet's gravity to help fling the spacecraft onward, and they seized that opportunity. Voyager 1's mission was supposed to last only 5 years, focusing on Jupiter and Saturn. Nobody imagined that it would keep going for decades, let alone become our farthest human-made object in space. One especially tense moment came at liftoff. The rocket carrying Voyager 1 nearly ran out of fuel just a few seconds before it reached orbit. Had it failed, the entire mission would have ended right there on the launch pad. Yet it made it into space, and from that moment on, Voyager 1 set out on a path to become the fastest and most distant spacecraft we have ever built. It reached speeds of around 38,000 miles per hour, vaulting past its twin. This speed helped it race through the asteroid belt, a place once thought to be too dangerous for any probe to pass, and continue far beyond the planets it was meant to study. The rocket engineers had packed Voyager 1 with instruments to survive extreme conditions, but nobody expected it to last this long or travel so far. Powered by plutonium generators, it never needed sunlight for energy, which was crucial as it zoomed farther and farther from the sun. Its speed and clever trajectory design allowed it to gather an incredible amount of data in record time. On the way, it made groundbreaking discoveries about Jupiter, Saturn, and their moons, snapping close-up images that changed what we knew about these distant worlds. But it wasn't just about going fast. Voyager 1 also carried a small piece of art and culture in the form of the Golden Record, which holds sounds and music from Earth. This tiny disk still sails through space, riding along with the spacecraft on its incredible journey. That journey all began with a daring launch, a brush with an empty fuel tank, and a burst of unexpected speed that propelled Voyager 1 into the history books. Even after so many years, its launch story remains a shining example of human courage, ingenuity, and the thrill of exploration. Jupiter became the center of attention when Voyager 1 provided our first true close-up look at the massive gas giant in 1979. Although NASA's Pioneer spacecraft had passed by earlier, the Voyager mission revealed Jupiter in ways no one had witnessed before. From millions of miles out, the probe's cameras started taking stunning images of the planet's swirling clouds, its faint ring system, and even its largest moon. As Voyager 1 drew closer, scientists back on Earth were amazed to see Jupiter's dynamic atmosphere in greater detail. The famous Great Red Spot, a gigantic storm bigger than Earth itself, came into sharper view. Prior to Voyager, many people simply pictured Jupiter as a striped orb, but the new photographs revealed that Jupiter's clouds move in intricate swirls and eddies, with lightning-like flashes and dramatic color variations. These swirling patterns showed just how active and changeable the planet's weather can be. Voyager 1 also detected a faint ring system around Jupiter. This discovery surprised many because rings were mostly associated with Saturn at the time. Though Jupiter's rings are much thinner and dimmer, Their existence proved that ring systems might be more common among large planets than previously thought. In addition, the spacecraft found 2 new Jovian moons, Thebe and Medes, bringing more excitement to an already thrilling mission. Perhaps the biggest shock came from Jupiter's 4 largest moons, the Galilean satellites. Particularly, Voyager 1 witnessed the incredible volcanic eruptions on the fiery moon Io. In fact, this was the first time scientists had spotted active volcanoes on another body in our solar system. Volcanoes shot plumes of molten material hundreds of miles into space, reshaping our understanding of what a moon's surface could be like. Another major revelation involved Europa, whose smooth, icy exterior hinted strongly at a hidden ocean below, fueling hopes that it might harbor conditions suitable for life. All these discoveries changed our view of Jupiter forever. From wave after wave of cloud formations to volcanic outbursts on Io, Voyager 1's encounter transformed the planet from a fuzzy disk in telescopes to a complex system filled with surprises. This first close-up look at the largest planet in our solar system did more than just gather lovely pictures. It reshaped our knowledge of planetary processes. The mission also set the stage for further exploration of the outer solar system, proving that beyond each major finding, there might be even more wonders waiting in the darkness for bold explorers to find. Volcanic eruptions on Io were one of the biggest surprises revealed by the Voyager 1 spacecraft when it visited the Jupiter system in 1979. Before that, scientists thought most moons, much like Earth's moon, would be ancient, crater-pocked landscapes. Yet Io completely upended those assumptions. When Voyager 1 flew past, it captured startling images of giant volcanoes erupting and spewing hot material high above Io's surface. These eruptions shot sulfur-rich plumes hundreds of kilometers into space, proving that Io was not only geologically active, but also the most volcanically active body in our entire solar system. Much of this volcanic activity is powered by Io's special relationship with Jupiter and 2 of its neighboring moons, Europa and Ganymede. As Io orbits Jupiter, it gets tugged and stretched by the combined pull of these other large bodies. This constant squeezing generates enormous heat inside Io, melting rock and driving the frequent eruptions. In fact, Io has so many volcanoes that it is estimated that its whole surface is replaced by fresh lava flows every few million years. This is unlike anything we have ever seen elsewhere. The plumes themselves often take on stunning forms. In some photos, big umbrella-shaped clouds spread out at the top of the eruption, kicked up by volcanic vents below. A closer look shows reddish, yellow, and white patterns painted across Io's landscape. These colors come from different sulfuric compounds, giving Io a colorful, even psychedelic surface appearance. Because of this, Io has been called a pizza moon, as the swirling patches of sulfur resemble toppings on a pizza. Voyager 1's discovery of active volcanoes utterly changed our understanding of how moons work. It revealed that small worlds with enough tidal forces acting on them could sustain volcanic activity. Later missions like Galileo confirmed that many of Io's eruptions reach incredible heights and vary in style. Some vent material in steady fountains, while others blast out in violent spurts. Over the years, scientists have tried to model how Io maintains such high levels of volcanism. Data suggests a molten or partially molten layer deep inside, continuously feeding eruptions. Even though Io lacks large amounts of water, this strong tidal heating proves that life on a moon is not just about having an energy source. There must also be the right conditions, which Io sadly lacks. Still, Io's volcanoes help us understand tidal forces, geological change, and how other moons might behave. Thanks to Voyager 1's bold journey, we discovered that our solar system still has hidden wonders, and Io stands out as a fiery little world forever reshaping its surface. Europa, one of Jupiter's largest moons, has long captured people's interest because of clues that it might shelter an ocean beneath its icy shell. The idea first arose in the late 1970s when NASA's Voyager 1 took close-up images of Europa's smooth, nearly crater-free surface. Instead of showing deep gashes from meteor strikes as on many other moons, Europa's exterior displayed crossed lines and ridges suggesting active geological processes. Scientists theorize that these cracks formed due to a layer of water or slushy ice underneath that could move and shift the crust. The possibility of liquid water caught the attention of researchers looking for places in the solar system that might support life. Water is a vital ingredient for life on Earth, so finding a hidden ocean beyond our planet is deeply exciting. Further missions like Galileo, which arrived at Jupiter in the mid-1990s, strengthened the case for Europa's buried ocean. Galileo detected hints of a magnetic field tied to Europa, something that could come from a large body of conductive fluid. This strongly indicated a saltwater ocean beneath tens of kilometers of ice. Although nobody has drilled through Europa's surface yet, the evidence has piled up over the years. Measurements of the moon's density also fit the idea of a rocky core, topped by an outer shell of water, or ice, about 100 kilometers thick. Within that shell, many scientists think there's a deep global ocean that may hold more liquid water than all of Earth's oceans combined. Plus, Europa's core likely produces heat through tidal flexing. As Europa orbits Jupiter, it is stretched and squeezed by Jupiter's powerful gravity. This generates internal warmth, which keeps the ocean from freezing solid. Most compelling are the occasional glimpses of plumes. Some spacecraft observations hinted at water vapor jetting into space from cracks in Europa's surface. If confirmed, these plumes might allow future robots or orbiters to sample the moon's ocean indirectly by tasting the vapor. Such a mission could reveal whether the hidden ocean contains elements essential to supporting life. Europa's possible ocean remains one of the biggest draws for space exploration. Future missions like NASA's Europa Clipper aim to fly close and map the moon in unprecedented detail. They will test whether Europa's ocean truly exists and investigate if it harbors the right conditions for life. From cracks in ice to potential plume activity, this distant moon keeps surprising us. If water is indeed present below the surface, Europa's ocean could become a new frontier in the search for life beyond Earth. Saturn offered a grand spectacle when Voyager 1 arrived in November 1980, followed by Voyager 2 in August 1981. Scientists were already intrigued by the planet's wide rings, but Voyager's up-close images exposed a far more complex ring system than expected. Instead of just a handful of broad rings, there were hundreds of thin ringlets, each containing icy particles and dust. The faint fringing first noticed by NASA's Pioneer 11 only a year before surprised everyone with its braided appearance, maintained by two shepherd moons called Prometheus and Pandora. Through its cameras, Voyager also found additional moons, such as Atlas, and provided clear views of previously known ones, each with its own unique story woven into Saturn's orbit. Yet the biggest mystery turned out to be Titan, Saturn's largest moon. Both Voyagers detected that Titan was wrapped in a thick orange haze, making it impossible to see the surface below. Measuring Titan's atmosphere revealed that it was primarily nitrogen, much like Earth's, but far colder and laced with other molecules that give the moon its hazy glow. In fact, Titan's thick clouds blocked all visible light images of its surface, leaving scientists with nothing but questions. Was it covered in oceans made of methane? Would there be lakes, rivers, or even a landscape shaped by liquid hydrocarbons? Voyager's data hinted that something dramatic lay beneath the fog, but no one could say for certain without more direct observations. Saturn itself still stole the show, though. Colorful photographs showed pale yellows and muted browns in its upper clouds, shaped by winds that sped around the planet at hundreds of miles per hour. The spacecraft also recorded polar regions that differed from the equatorial zones, hinting at the complexity of Saturn's weather systems. Captivating features called spokes were spotted, moving across the rings, defying simple explanations. Scientists suspected that these ghostly marks might be triggered by electromagnetic forces, but the complete picture was still unclear. When Voyager 1 finished its encounter and swept behind the ring planet, its flight path tilted it upward out of the ecliptic plane, setting it on a course toward interstellar space. Meanwhile, Voyager 2 used Saturn's gravity in a different way to continue its grand tour, aiming for Uranus and Neptune beyond. In the end, Voyager's close brush with Saturn enriched our understanding of ring dynamics, unveiled several new moons, and drew global attention to Titan's hidden realm. Those few days near Saturn remain some of the most enthralling in the history of space exploration. On February 14, 1990, Voyager 1 turned its camera back toward Earth from an astounding distance of about 6 billion kilometers. The resulting photograph, famously called the pale blue dot, became one of the most iconic images ever taken during space exploration. In this photo, Earth appears as a tiny speck, just a fraction of a pixel, suspended in a sunbeam. Despite being so small, that faint dot is our entire world. Everything we know, every story, every person, every life, captured in a single pinpoint of light. This image happened almost by chance. The team operating Voyager 1 knew the spacecraft was about to have its cameras switched off forever to conserve power for the long journey into deep space. Inspired by a suggestion from the late astronomer Carl Sagan, they decided to take one last look homeward. Nobody could have guessed that a barely visible speck in a shaft of sunlight would come to carry such deep meaning for so many people. When the first data reached Earth, scientists and the public were deeply moved. The sight of our planet as a nearly invisible dot in the vast blackness of space sparked profound reflections on the fragility of life and our shared responsibility to protect our home. The pale blue dot image is more than just a photo. It's a mirror. It invites us to step back from our lives and consider our place in the cosmos. From such a distance, Earth isn't divided by borders, politics, or religions. It's just a single glowing pixel, isolated in the void. As Carl Sagan famously wrote, "This dot is the only home we've ever known." By the time Voyager 1 captured that haunting image, it had already completed flybys of Jupiter and Saturn, and it was sailing far beyond the planetary realm, heading into the unknown. Nobody expected the spacecraft to survive for so many decades, yet its final image of Earth still resonates powerfully today. It represents the fragility of our planet, the fleeting nature of existence, and the unity of all people who share this one pale blue dot. The phrase pale blue dot has since come to symbolize humility. It reminds us that while our problems may seem enormous, they're minuscule on the cosmic scale. And above all, it underscores the idea that we are all passengers on the same tiny world. We share this fragile speck in an endless universe, and the truth should encourage us to care more deeply for each other and for the Earth itself. Years later, the pale blue dot remains one of the most powerful statements about humanity's place in the cosmos. It doesn't need loud declarations or dramatic imagery to move hearts. Its quiet, understated presence says everything it needs to about perspective, wonder, and the enduring mystery of existence. Crossing into interstellar space was another historic moment for the Voyager mission, one that marked humanity's first foray beyond the protective bubble of our solar system. For decades, both Voyager 1 and 2 had been traveling outward, silently slipping through the outer boundary regions of the heliosphere, the vast zone dominated by the solar wind and magnetic field of our sun. Their first major milestone in this transition was the termination shock. This is the area where the sun's fast-moving solar wind slows down abruptly as it begins to interact with the much cooler and denser environment of interstellar space. Beyond the termination shock lies the heliosheath, a turbulent, chaotic region where the solar wind piles up against the interstellar medium, much like water pressing against a dam. Scientists once imagined this layer as smooth and steady, but Voyager revealed it to be far more dynamic and irregular than anyone expected. Eventually, both spacecraft reached the heliopause, the outer boundary where the sun's influence finally fades and the environment of interstellar space begins. On August 25, 2012, Voyager 1 crossed this threshold, becoming the first human-made object to enter interstellar space. There were no breathtaking images to mark the moment, as Voyager 1's cameras had been turned off long before. Instead, the crossing was confirmed through data that showed a sudden drop in the number of solar particles and a sharp rise in high-energy cosmic rays coming from outside the solar system. The surrounding plasma density also changed, confirming that Voyager 1 had passed into a new domain. But this discovery wasn't instantly recognized. It took nearly a year of careful analysis for scientists to confirm that Voyager 1 had truly crossed the heliopause. One reason was that the magnetic field direction, expected to shift noticeably at the boundary, didn't behave as predicted. This puzzling data delayed confirmation and challenged models of the solar system's outer edges. Voyager 2, traveling on a different path, would give researchers a second chance to observe this elusive boundary. On November 5, 2018, Voyager 2 crossed into interstellar space as well, providing a new set of measurements. Surprisingly, it entered at almost the same distance, about 120 astronomical units from the Sun, even though the crossing occurred 6 years later and during a different phase of the Sun's activity cycle. This consistency offered scientists a new clue about the structure and behavior of the heliosphere's edge. The transition into interstellar space didn't mean the spacecraft had left the solar system entirely, as they still remain within the Sun's gravitational reach and far from the Oort cloud, the distant shell of icy bodies that marks the true boundary. But scientifically, it was an enormous leap. For the first time, humanity had a presence in the space between the stars. These lonely probes, small and silent, continued to send back precious data about cosmic rays, magnetic fields, and plasma density in regions never before explored. And all the while, Voyager 1 and 2 drifted farther and farther away from Earth, pioneers of a journey no other spacecraft had ever taken. They became ambassadors of our civilization, each carrying a golden record, a time capsule of sights, sounds, and greetings from Earth, designed for any potential beings who might one day find them. These findings exposed a complex and ever-changing region shaped by the constant battle between the solar wind and cosmic particles from the rest of the galaxy. The pressure of the solar wind shifts over time with the Sun's activity cycle, pushing back against interstellar materials and creating a constantly fluctuating frontier. While crossing the heliopause was an incredible scientific milestone, it's important to note that neither Voyager 1 nor Voyager 2 has actually left the solar system. That broader exit won't happen for another 30,000 years or so, when the probes will finally pass beyond the Oort cloud, a distant spherical shell of icy bodies that encircles the solar system far beyond the orbit of Pluto. Until then, the Voyagers continue their silent journey into deep space, their signals growing ever fainter, but still carrying valuable insights about the interstellar medium. Even as they gradually lose power and edge toward the ends of their operational lives, they remain symbols of our relentless curiosity and our yearning to explore the unknown. Their distant whispers remind us of just how vast space truly is, and how much more remains beyond the reach of even our most advanced machines. Among the most intriguing surprises from the Voyager missions were the unexpected magnetic field findings. Before Voyager 1 crossed the heliopause in 2012, scientists had widely assumed that it would detect a distinct and sharp change in the magnetic field direction. It seemed logical. The heliosphere, dominated by the Sun's magnetic influence, should end at a clear boundary, giving way to the interstellar magnetic field, which presumably came from a different direction entirely. But what Voyager 1 observed didn't match that expectation. Although the spacecraft detected a sudden increase in particle density and a dramatic spike in cosmic rays, both strong signs that it had entered interstellar space, the magnetic field direction barely changed. Instead of an obvious shift, the orientation remained nearly the same, puzzling researchers and sparking heated debate within NASA. It took almost a year of analyzing data to finally confirm that Voyager 1 had indeed crossed into the interstellar medium, despite the unexpected magnetic readings. 6 years later, when Voyager 2 followed on a different trajectory and passed through the heliopause on the opposite side of the Sun, it too encountered only a mild shift in magnetic field direction. Once again, the anticipated clean divide between the solar and interstellar magnetic fields failed to appear. This consistency between both probes suggested that the boundary region was far messier than predicted. Instead of a neat transition with opposing magnetic lines, the heliopause appeared more like a tangled mix, interwoven, distorted, and unpredictable. That both Voyagers crossed the heliopause at about the same distance from the Sun, roughly 120 astronomical units, even during different phases of the Sun's 11-year cycle, added another layer of surprise. These observations are forcing scientists to revisit and revise long-held assumptions about how our solar system interacts with the broader galaxy. Maintaining communication with spacecraft that are billions of kilometers away is no small feat. The Voyagers each transmit with a power of just about 20 watts, less than a common light bulb. By the time their signals reach Earth, they are unimaginably faint, measuring at a fraction of a billionth of a watt. Capturing and decoding such a signal requires one of humanity's most sensitive and sophisticated communication systems, NASA's Deep Space Network, DSN. The DSN consists of enormous radio antennas located in 3 regions around the globe: California, Madrid, and Australia. This global positioning ensures that, as Earth rotates, there's always at least one station with a clear line of sight to the spacecraft. Each station listens attentively for Voyager's signal and shares its data with scientists around the world. To maintain that fragile connection, the spacecraft must keep their 3.7-meter-wide high-gain antennas precisely aimed at Earth. That's where the onboard attitude and articulation control subsystem comes in. This system constantly checks the positions of stars to determine the spacecraft's orientation and makes small adjustments to keep the antenna perfectly aligned. Any misalignment could send the signal drifting into empty space. Each Voyager is powered by radioisotope thermoelectric generators, or RTGs. These devices convert heat from the radioactive decay of plutonium into electricity. At launch, they provided enough power for all instruments, but over time, the energy output slowly declines. That gradual loss of power forces mission engineers to make difficult decisions, choosing which instruments to keep running and which to shut down in order to extend the mission's life. It's a constant act of triage, carefully managing dwindling resources to ensure the probes can continue sending back valuable science. Over the years, engineers have become experts at adapting to unexpected challenges. Sometimes a computer on board the spacecraft glitches or a thruster misfires. Because each command takes more than 20 hours to reach the spacecraft, and just as long for a reply to come back, even a minor correction can take days. Every decision must be deliberate, every move meticulously calculated. And yet, time after time, the mission teams have risen to the challenge, patching software, switching to backup systems, and reconfiguring operations to maximize science output with minimal power. Perhaps one of the most memorable recent challenges occurred in November 2023. Voyager 1 suddenly fell silent. The data it returned was unintelligible, just a garbled stream of binary code. It seemed as though the spacecraft had suffered a fatal malfunction. With no clear signal and no straightforward diagnosis, it appeared that Voyager 1's journey might be over. But the team didn't give up. They combed through every previous transmission, trying to pinpoint what went wrong. Eventually, after months of tireless effort, they discovered a faulty memory location in one of the spacecraft's onboard systems. Using a carefully crafted sequence of commands, they managed to reroute functions around the glitch. Against all odds, Voyager 1 began sending usable data once again. It was a triumphant reminder that, even after nearly 50 years in deep space, the mission is still alive, still contributing to science, and still embodying the very best of human ingenuity and perseverance. The core of this issue was found deep within the flight data system's memory. Engineers eventually discovered that specific code blocks had become corrupted, likely the result of cosmic radiation or simple wear from decades of operation in space. The solution they devised was both simple in concept and incredibly complex in execution. Move those code blocks to a new region of memory that still functioned correctly. That might sound straightforward, but when you're talking about reprogramming a spacecraft launched in 1977, it's anything but. It wasn't until April 2024 that they began cautiously transmitting the necessary commands to shift the code. Each one took 22.5 hours just to reach the spacecraft, and another 22.5 hours to get a response. Every command was a gamble, with no guarantees that Voyager 1 would understand, let alone execute, the instructions. But after months of silence and 5 long months of effort, the spacecraft finally answered back. 2 days after the final command sequence was sent, usable data began returning once again. Contact was reestablished, proving once more the power of persistence and ingenuity. Another incredible example of Voyager's durability came years earlier in 2017 when engineers faced declining performance from Voyager 1's main attitude control thrusters. These tiny jets, essential for pointing the antenna at Earth, had gradually degraded after decades of use. With options running out, the team made a bold choice. They decided to attempt a switch to the Backup Trajectory Correction Maneuver Thrusters, or TCM thrusters. These had been unused since the early 1980s during the Saturn flyby and hadn't fired in over 35 years. There was no certainty that these long dormant components would still function. But when they finally sent the command, something remarkable happened. The TCM thrusters responded perfectly, firing on cue and allowing the spacecraft to reorient itself once more. It was a stunning testament to the quality and resilience of the original engineering. That same blend of careful planning and daring creativity has been key to every stage of the Voyager missions. As power levels continued to drop over the years, engineers were forced to shut down more and more systems. Instruments were turned off one by one, heaters were cut, and once active subsystems went cold. Yet with each reconfiguration, the team managed to extend the Voyager's operational lives, squeezing out a bit more time, a bit more data, a few more discoveries. Even now, as the last instruments are prioritized and the end of power draws near, the Voyagers remain operational, still venturing farther from home than anything else humanity has built, still whispering back their tales from the stars.